Hi everyone. Good morning. Welcome back to Semicon Technolabs YouTube live presentation today. So, technical topic is synthesis in VLSI Part 3. So, previously we discussed about synthesis in Part 2 and Part 1. So, let's recap what we discussed in Part 3 and Part 2 and Part 1. Okay, so synthesis, as we know in the ASIC flowchart, so synthesis is coming in the front end part of the ASIC flowchart, where like initially we will be having the design, and once the design is functionally verified at the um, functional simulations, then the design is given as input. Design is nothing but RTL code in any of the HDL languages. It can be Verilog or VHDL. So the RTL code is given as input, the structural RTL code, which is passing the functional simulations. This is given as input to synthesis tool in order to map it into technology dependent gate level netlist. Now let's dive into synthesis in VLSI part 3. So let's go through the topic. The main objective of the part 3 is to explain synthesis flow and post-synthesis netlist quality checks. In ASIC flow, synthesis is the part of front-end design, while the back-end design takes the synthesized netlist as an input. So the synthesized netlist should meet all netlist quality checks to reduce multiple iterations, right? Which reduces the turnaround time and efforts, right? Now, let us see how synthesized netlist by meeting the netlist quality checks will reduce the number of iterations, multiple iterations, because if the synthesized netlist is not able to meet the design rule constraint requirements, for example, max tran, max cap, max fan out, or let's say if the synthesized netlist is not able to meet the setup timing requirement, then in both the cases it will lead to multiple iterations, because in physical design it will be difficult to take the synthesized netlist forward. Similarly, let's say if we are targeting for power and area, if the area number of the synthesized netlist is big, then even in that case as well, it becomes difficult to take up this netlist forward, because the area number will not be possible to fit in the given die size of the physical design. Similarly, if the power numbers, it can be leakage power, it can be dynamic power. If the total power numbers are difficult to meet in the design, for example, at the PNR stage, it is very difficult to reduce the power numbers further. And if these power numbers are crossing the power budget values given by the customer, then even in that case as well, the netlist has to be resynthesized, which will lead to multiple iterations again in order to reduce the power consumption. Similarly, congestion. If we are doing physical aware synthesis, even in physical aware synthesis, when we enable the congestion and try to replace high pin porosity cells with low pin porosity cells, even in those cases also, if the congestion optimization is not done properly, in that case also the congestion will pop up in physical design, and which will be difficult to close in physical design, which will again lead to multiple iterations in synthesis to replace high pin porosity cells with low pin porosity cells for minimizing the congestion, right? Now, we will see the overview of various checks that are performed at the synthesis stage of the ASIC flow in this article. After reading this article, you will be able to answer the following questions. What is synthesis? Why do we need synthesis? What are the input and output of synthesis? What is synthesis flow? What are the checks performed to ensure the netlist quality? Right? Introduction. What is synthesis? Let's recap what is synthesis. So synthesis transforms the RTL. RTL is nothing but register transfer level code of design modules into gate level netlist, right? So this gate level netlist is technology dependent, which means based upon the technology node which we have provided and the PDK files which we have provided related to that technology node. It can be timing library files, that is PVT files containing the timing information, area information, leakage power information, internal power dissipation information, lookup table information in order to come up with the cell delays, design rule constraints information, which can be max tran, min capacitance, max fan out, So considering the PVT library related to that technology node, the cells are picked up from the PVT library, and accordingly the RTL, which is register transfer level, is mapped into technology dependent gate level netlist, right? So this process is called as synthesis, right? So here our agenda is to make sure that this technology dependent gate level netlist is meeting all the PPA requirements, that is power, performance and area. Nowadays it is called as power, performance, area, congestion, schedule, because congestion is equally important in our technology nodes to make sure that the netlist which we are providing, this netlist is able to meet the congestion requirements of the physical design, and we are able to route the design. Similarly, the netlist which we are providing from synthesis, it should help us to close the physical design within the allocated schedule, so that overall schedule can be met. So finally, the synthesis is responsible for PPACS, that is power, performance, area, congestion, schedule. So this stage performs logic, area, power optimization and scan insertion, right? So we do the logical optimization, which means in the data path of the netlist, right? The data path is well optimized. It doesn't have high pin porosity cells. It doesn't have high drive strength cells, right? It is going in a balanced way with respect to do use and don't use list that is being used in synthesis, right? So that way the logic that is defined in the data path, this logic is helpful in meeting the power, performance and area, right? When I say performance, it is nothing but timing, right? And similarly, it should be able to map the functionality properly, right? That is equally important. So whatever the functionality that is present in the RTL has to be mapped properly into the logic. Now second thing, as I mentioned, is area, right? The area numbers should be reasonable, because these are the area numbers along with bloat factors. When I say bloat factors, we need to also accommodate for increase in area due to addition of cells. Either it can be during placement stage of physical design, where we add the buffers and inverter pairs, normal buffers and inverter pairs, in order to meet the DRVs. It can be pre-placed cells like well taps, end caps, which we add in the floor plan stage, or it can be clock tree related cells like clock buffers and clock inverter pairs, which we add to build the clock tree, or it can be delay cells which we add to optimize the hold, right? Now, power optimization. The power optimization is always related to leakage power and dynamic power. So when we are doing PG mesh, at that time we have to look into the leakage power optimization. Similarly, when we are going through the flow, right, I mean when we add the cells during placement, CTS, routing, based on the cells placement and how many cells are getting added, that time we have to make sure that the dynamic power is coming under control. Again, in dynamic power we have switching power and internal power, right? So the power optimization has to be taken care, right? As we discussed in the previous synthesis in VLSI part 2 and part 1, that we are using clock gating technique in order to reduce the power optimization, right? Similarly, scan insertion. So in synthesis, we don't deal with MBIST, we don't deal with JTAG, but however, replacing the normal flop with scan flop is performed here, so that the scan flop delays can be accounted when doing the scan optimization. For example, when we do the scan stitching, like scan in and scan out connected to each of the scan flops, we need to make sure that this scan insertion is helping in meeting the scan timing, right? When in the test mode, when we supply the test clock. Similarly, during normal operation, that is during the functional operation, we need to make sure that with the functional clock, we are able to close the timing in the given clock period by using the scan flops which are having slightly higher cell delays, including the clock to queue delay, right? So that is the need, I mean that is where the need has come to have scan insertion done during the synthesis stage itself, right? Now, various tools are available which can be used to do synthesis, such as Synopsys Design Compiler, Synopsys Fusion Compiler, and Cadence Genus, right? Now, Synopsys Design Compiler, we use Synopsys Design Compiler when our backend tool is different. For example, if we use backend tool as Synopsys ICC2, if we use Cadence Innovus tool, then in those cases we depend on Synopsys Design Compiler, right? But however, if your backend also is Synopsys, and if we are planning to use Fusion Compiler, then it is always advisable to use Fusion Compiler. The reason being, it is a single graph based tool where the same Fusion Compiler can perform synthesis as well as backend, right? And similarly, Cadence Genus. So Cadence Genus is another wonderful tool from Cadence where like we can perform the synthesis operation. Okay, and backend can be, again, it can be Cadence Innovus, or it can be Synopsys Fusion Compiler, or it can be Synopsys ICC2. Okay, so these are the different tools that are available. But however, please note that for power optimization, only design compiler or Fusion Compiler is not sufficient. We need to have Synopsys Power Compiler license also in order to perform the power optimization. Similarly, in order to perform the DFT optimization or scan insertion, we need to have Synopsys DFT compiler also. So these are additional licenses which we need along with the regular compiler licenses which we have from Synopsys for doing the synthesis optimization. Okay, now with this, let's go to the synthesis overview, right? So once the RTL of the design fulfills all the criteria of RTL checks, right? What do we mean by RTL checks? So the RTL checks mean the RTL, register transfer level, which is either written in HDL language of Verilog or which is either written in the HDL language of VHDL. So these two RTL files or any of the RTL files have to meet the functional requirement. And how do we make sure that the functional requirement is met? Only when, right? Only when we have RTL meeting the functional requirements in the dynamic simulations. Okay, only then we can say that the RTL is meeting the functional requirements, right? Similarly, the RTL should be free from any kind of lint issues. Okay, so the RTL should be understandable by the synthesis tools. There should not be any lint issues. There should not be any syntax issues. There should not be any missing RTL files, right? So once all the RTL checks are clean, then the next step is synthesis, right? So in synthesis, synthesis is the stage where the RTL code is converted or mapped into gate level netlist. Synthesis is one of the important steps in chip designing flow, as it allows us to visualize the design as it will appear after manufacturing. For example, in RTL, we can only see the assign statements as we discussed in the previous synthesis sessions, right? Now, once the synthesis netlist is available after mapping the RTL into gate level netlist, you can clearly see how the assign statements are mapped into combinational gates, and in the schematic view, you can clearly see how the combinational gates are connecting to each other, right? So that way it will give a visualization of the design after as how it will appear after manufacturing, right? So here the designers review all reports and validate all required factors, including timing, area, and power. So designers can make necessary changes if required before the creation process, which saves time, money, and effort, right? So while dumping out the gate level netlist in synthesis, we have the power of decision making where we can judge if the technology dependent netlist is able to meet our timing requirement, if it is able to meet our area requirement, is it able to meet our power requirement, right? Only when timing, area, and power requirement can be met by the technology dependent netlist, then we can move forward and have this RTL file mapped technology dependent netlist taken for other steps. It can be to add the DFT with respect to MVIST and JTAG logic, or if DFT is optional in the program, then directly we can map this technology dependent netlist into physical design, right, where it will be mapped into layout view, that is nothing but GDS2 or OSS. Okay, now as we know, synthesis process can be divided into three stages: translation, optimization, and mapping, right? Now let's see what is translation, right? So translation is the process to convert Verilog or VHDL design into structural representation, that is nothing but GTech cells that are technology independent. This is translation. Okay, so translation in one sentence, if we have to tell, translation means mapping the RTL into GTech netlist, which is technology independent netlist, right? This is translation. Now, what is the advantage of translation? We will have first cut technology independent netlist, which will give us idea whether RTL can be completely mapped into a netlist format. If at all we have any RTL issues, the RTL which cannot be mapped into technology independent netlist, then in that case we have to send back the RTL to the RTL team and get it updated so that it can be mapped into GTech netlist, right? So all the RTL related open items can be addressed here during translation stage. Okay, and even we will make sure that during translation the parameters that are set in the RTL are also mapped properly. Okay, then next is optimization. In this step the design gets optimized as per the required specification, right? So during optimization, based upon our PPA requirements, power, performance and area requirements, the optimization is performed, right? So during optimization, we can clearly see how much of area reduction has happened without compromising on the functionality, how much power reduction has happened, how much improvement in performance has happened, are we able to meet the clock frequency requirement of the design. So all those things can be understood during optimization stage. Finally, mapping. In this step, the structural design generic cells are mapped to technology dependent cells that have functional and timing information. So this is where you will have the final technology dependent gate level netlist, right, which will be taken forward for either DFT, MBIST insertion and JTAG insertion, or we can take this technology dependent gate level netlist into final PNR, right? Okay. Now let's see what are all the different inputs and outputs we have. Okay, synthesis inputs and outputs. Input, timing library. These are all the inputs. Timing library. It can be in .lib format or .db format based upon which tool you are using. Whether you are using synthesis synopsis tools or whether you are using synthesis cadence tools, right? So synopsis tools will be using .db file, whereas synthesis cadence tools will be using .lib file, right? If you are using fusion compiler in synthesis from synopsis, then you will be using NDM files, new data model files, right? Then physical library, it can be LEF and Milky Way. So Milky Way nowadays we are not using, it's a very old format which we used to use in ICC, right? So preferably we depend on LEF or NDM files, right, based upon again which tool you are using. So physical library is used for physical aware synthesis. Then SDC file, which is coming from RTL team, it is initially in the tickle format. It contains very basic information like create clock, create generated clock, timing exceptions. It doesn't contain DRC related constraints, that is nothing but max stand, max cap, max fan out. It doesn't contain interface timing, that is set input delay and set output delay, right? So those things, set uncertainty, right, design margin. So all these things are not present in the SDC file given initially to the synthesis team, right? And RTL, of course, it has to come from the design team, but please make sure that RTL is functionally clean. There are no issues associated to RTL, right? If in case RTL is expected to increase, right, in size in the next phases of the project, please make sure that you have enough area kept in your physical design, so that increase in RTL, which will again increase the size of the netlist, will be able to accommodate in the additional area that has been kept, foreseeing the increase in RTL, right? So that way you don't have to come back again and increase the die size of the physical design if you can follow this simple step. Okay, then def file, design exchange format file. This is used for physical aware synthesis. So it is called as two pass synthesis. So first pass, we just give the netlist from the logic aware. It is taken by the physical design team, and physical design team, so they will prepare the floor plan and they will provide us the floor plan def, which is used for again doing the synthesis, and but this time we are doing physical aware synthesis. So that is why it is called as two pass synthesis. Physical aware synthesis is called as two pass synthesis. Then TLU plus files, right, and QRC files for cadence. So TLU plus files, we use it for net delay extraction. RNC values are extracted in physical aware synthesis using TLU plus files. If TLU plus files are not present and if we are doing logic aware synthesis, then we depend on wire load models. Similarly, QRC files. So QRC files are given for cadence tools, and UPF. UPF is for synopsis tools and CPF is for cadence tools. Now outputs. What are the outputs of synthesis? It is technology dependent gate level netlist, UPF or CPF based upon which tool you are using, then SDC file, the final SDC file which contains set drive, set driving cell, set load, set input delay, set output delay, timing exceptions, set false path, set multi-cycle path, set min delay, set max delay, design margin, set uncertainty, right? And then set max transition, set max capacitance, set max fan out, right? So all these things are defined in the SDC file, final SDC file, which is going as input to physical design. Then def file. If in case the input def file has been updated by the physical aware synthesis team, right, then that def file has to be given as input to the physical design team. That is where you are dumping out the def file again. But however, if there is no change in the def file that is given as input to the physical aware synthesis team from the PD team, then in that case we don't have to give back the def file because there is no change and physical design team is already having the def file, right? So reports, right? I mean all kinds of reports with respect to power, performance and area, right? What is the goal of synthesis? Let's look at the goal of synthesis. Logic optimization with good QOR, quality of results, scan insertion, that is nothing but design for testability, netlist generation, that is nothing but technology dependent gate level netlist, then logical equivalence check, right, should be preserved between the RTL and netlist, right? Now, these are some of the goals. So, LEC has to be clean between the RTL and netlist. Now, types of synthesis, logical synthesis. Logical synthesis is a conventional synthesis that processes the HDL, Verilog or VHDL design and generates gate level netlist, right? During this process, the compiler optimizes the design based on predefined constraints, right? So this is logic synthesis, right? Now, physical aware synthesis, right? Physical aware synthesis requires additional floor plan def as an input. Floor plan def contains physical information like IO ports placement, macro placement information, blockages information. It can be placement blockages where like again we have hard placement blockage, soft placement blockage, partial placement blockage. So it can be any of these three different types of placement blockages which we use to minimize the congestion in the floor plan def, right? And die area information. Die area information means what is your die area, what is your die shape, how much of the core to die distance has been kept, right? And if you are putting any PG mesh, even the PG mesh information also can be placed in the floor plan def, which is given as input to the physical aware synthesis. You can also place well taps and end cap cells so that the floor plan def is complete, and physical aware synthesis tool can use the leftover core area in order to place the standard cells as per the floor plan, right? And if in case the physical aware synthesis team is not able to close the timing, then they have liberty to modify the floor plan def and provide the updated floor plan def to the physical design team so that they can take it forward. Additionally, we use RC coefficient files as one of the inputs to compute a more accurate wire delay values compared to the wire load model method, right? Now, what are the advantages of physical aware synthesis, right? Better PPA, power, performance, area. Better timing correlation with PNR. Better turnaround time. Reduces the number of iterations, right? So these are some of the advantages of physical aware synthesis. We definitely have an edge on the PPA, timing correlation and turnaround time. The reason being we are completely aware of the floor plan information that is present in the physical design. So whatever the optimization we do in synthesis, it is completely focused on the floor plan perspective, right? It will take care of the placement blockages and accordingly it will place the cells and do the DRC optimization, that is max tran, max cap, max fan out, and also setup optimization. Okay, that is the advantage, right? And easily it can correlate with the PNR because the same floor plan is getting used in the PNR. So there will be no change in the floor plan, no change in the power plan, no change in the pre-placed cells, right? And there will be no change in the overall die size and die shape as well. Okay. Now synthesis flow. So what is synthesis flow? Let's look at the flow chart. We are giving input RTL followed by LEF, followed by lib, followed by technology file, followed by UPF, DEF and SDC. right? And this is going as input to read design input, elaborate, compile, optimization, scan insertion, synthesis output, right? So these are the different steps what we have in synthesis flow. Okay, now let's look at more about this diagram. Synthesis inputs, lib file. The timing library contains .lib contains information related to the timing, power and area of the standard cells. It also contains different PVT characterization of the cells, right? Lef, library exchange format. Lef represents the physical information of metal and via standard cell and macro. RTL, it's a descriptive code written in HDL format. SDC, it represents the design constraint, right? Okay. Similarly, DEF, design exchange format. DEF file contains the placement information of macro pre-placed cells, IO ports, block size and blockages, mainly used for physical aware synthesis. UPF file is required to describe the power intent of the design, including the power domain, level shifter, isolation cells, and retention registers. These are all called as special cells, right, which are present in the UPF. The same type of special cells are also present in the CPF as well, which is common power format that is used by the Cadence tools, all the way from Cadence RTL tool till the final PNR tool. All the tools are compatible to use CPF files, right? Now, what is elaboration? At this stage, it reads the RTL code, and this RTL code is converted into modules as per its logical hierarchy. Once it has all logical Boolean representation loaded, the tool maps logic with a technology independent cell called the GTEC cell. During elaboration, the tool checks whether the design is unique. If not, it stops the tool. Once the design becomes unique, the tool checks for unresolved references in the design. If it has linking issues, then an RTL correction is required, or you need to check if it is due to any missing libraries. After elaboration, it checks for timing loops in design. Please make sure that there are no combinational timing loops in the design. If you find any timing loops, you need to get RTL correction done by the designer, because timing loops will not have endpoints. So then it becomes difficult to do the timing analysis, right? This is the drawback of the timing loops. So please make sure that you get it corrected at the designer side. Now compile and optimization. After elaboration, in the compilation stage, the tool maps the GTEC cell with the actual cell, specific technology dependent from the library. Actual cell mapping is dependent on the design constraints or user specific constraints. Apart from this, the tool removes the registers with constant propagation are unloaded, which are not required in the design. If these removed cells are required, then you need to provide feedback to the designer to get the correct RTL, right? After elaboration and compilation, the tool performs optimizations based on user constraints to meet timing, area, and power requirements. Right? This is compile and optimization after the elaboration step is done. Right? Next, DFT. DFT stands for Design for Testability. Okay, performs the scan insertion in the optimized design. After this stage, the design should fulfill the scan criteria and achieve the desired scan coverage. This is very, very important. Okay, scan coverage means the more scan coverage you have, the more controllability and observability we can have towards the DFT. Right? Controllability is for inputs and observability is for outputs. Okay, so that is how we have to define the scan coverage. Okay, scan is used for testing the standard cells. MPIST is used for testing the macros. JTAG is used for testing the IO pads. Okay. Outputs. A qualified netlist with scan insertion and good QOR in terms of timing, power and area. Other outputs are updated, DEF, UPF and SDC. Right? UPF, the output UPF is the updated version of the input UPF. At the synthesis stage, it performs logic optimization that introduces new power intents. So we are generating UPF with this update after synthesis, right? DEF. While performing physical aware synthesis, we also generate the DEF file which contains macro and standard cell placement information. This DEF is directly used in physical implementation that avoids placement of the cell from scratch. Hence, we can save runtime. SDC. The output SDC is the updated version of the input SDC. At the synthesis stage, we use constraints provided by the designer. Additionally, we use certain local constraints to improve the overall QOR of the design. Thus, the SDC with this update is generated after synthesis. Right? Now, what are the netlist quality checks? In the very beginning of this synthesis in VLSI part 3 presentation, we discussed about netlist quality checks, right? Without proper netlist quality checks being done, it will lead to multiple iterations, right? So we need to make sure that netlist quality checks are adhered properly, and we need to make sure that there are no netlist quality issues in the netlist that is getting delivered to the PDT. Okay, so below are certain checks that should be fulfilled post synthesis to ensure netlist qualifications before it is delivered for physical implementation. No clocks. In this check, we ensure that all the required clocks reach the sync pins, okay, CK pins. Some major reasons for getting no clock violations in the design are mentioned below. Clock definition missing. This is observed when clock creation is missing in the clock constraint file. Right, RTL connectivity issue or tie-up. This type of no clock is observed when there is missing connectivity in between modules in the RTL or having direct tie-ups in the RTL. Impact. How the no clocks will impact. Ideally, all registers in the design should be clocked. If no clock issue is left in the design, then it will report unconstrained endpoints and can cause optimization issues on such paths. Solution. To resolve the above mentioned no clocks violations, we need to get the corrected RTL from the designer and clock constraints files with all the required clock definitions. Command. You can easily check the no clock issues by using this command check timing -include no clock. Right? Then unconstrained endpoints. This is due to the missing IO constraints, clock definitions, or due to some exceptions at the sequential cells or ports. Possible reasons are case constant, no arrival path, or false path. Impact. If IO constraints are missing in the design, then the external launch time for the input path or the capture time for the output path will be missed. It can cause an incomplete timing check. If the path is expected to be false, it could lead to an incorrect timing check. Solution. To resolve these problems, we need the correct constraints file SDC, which defines all the required clocks used in the design. IO delays on all the required ports, verified false path and case constraints in the design. Command check timing -include unconstrained endpoints. This is the command for verifying the unconstrained endpoints. Next, timing. In this check, the entire design is divided into timing paths. For each timing path, the delay is calculated and checks violations based on timing constants. Clock period, clock uncertainty, setup time. The major reasons for having timing violations are levels of logic, incorrect or missing constraints such as clock relations, clock exceptions, and incorrect uncertainty. Impact. If a huge timing violation is reported at the synthesis, this violation will be difficult to fix at later stages, PNR or ECO, which also impacts the power and area. Solution. The techniques used to solve or reduce timing violations are user-defined path groups with appreciate weightage by disabling selectively or entirely multi-bit banking in design, bound creation, using timing efforts high or incremental compilation. If we are performing physical aware synthesis, it is expected to have a good macro placement that improves timing violations. What is the command? Report timing or report QR, right? Then next check, next netlist quality check, LEC. This is one of the important checks that validate the correctness of the netlist concerning the RTL. It is recommended to perform this check when there is an update in the RTL or netlist. Generally, in the synthesis LEC, a check is performed between the RTL versus synthesis netlist and synthesis netlist versus post-scan netlist. General issues due to which the LEC can fail are as follows. CSN missing. The missing CSN connect supply net can lead to LEC failure. Isolation cell mapping. When there is an issue with UPF constraint, then there could be a possibility of having different isolation cells mapped in between the RTL and synthesis netlist that may cause LEC failure. Undriven nets. If we have undriven nets in the RTL, the synthesized tool will tie off these nets, causing LEC failure. This can be resolved by getting the RTL fixed, or if the undriven is expected, then you need to use undriven constraints to pass the LEC. Constraint used for formality tool, which is synthesis tool, right? Set constants net name 0 or 1. Impact. If the LEC is not clean, then the equivalence is not maintained between the RTL and netlist, which can lead to functionality failure. EDA tools. Formality from synopsis, conformal from cadence. Timing loop. In the RTL, if in between combo logic, the output is again fed to the same input of combo logic that forms a logical loop. This loop is called the timing loop. We can get the timing loops due to RTL connectivity issues in design that which can lead to metastable data. Thus, we should avoid timing loops while netlist generation. In fact, the path with the timing loops will not have endpoints. If such loops are not broken, then the path will not be correctly timed. Right? This is very important. Solution. If we are getting timing loops that are expected to have, then in such case we need to use the constraint to break such timing loops. If such timing loops are not expected in the design, then we need to get the updated RTL command check timing hyphen include loops, right? Empty modules. If the RTL module definitions don't have any logical content such as wire inputs or outputs, then such modules are called empty modules. This check is performed before compilation. By default, empty modules are removed during synthesis. If we want to preserve this empty module, we need to apply constraint set don't touch on that module before compilation. Command is check design, which is a mega command. Removed flop. If the register is removed during compilation and optimization, then such flop is reported as removed flops. If the register is either unloaded or constant, then by default during compilation, such flip-flop is removed from the design. If such flip-flops are expected in the design, then we need to use certain constraints to preserve this. Report unloaded registers, report constant registers, right? Floating inputs and multi-driven pins. If the design in the design, there might be a possibility that a few of the pins are not connected to any element present in the design. Such pins are known as floating pins. While performing optimization, such floating pin cells might get optimized due to which there could be a breakdown in logic. Multi-driven nets are detected when there is more than one input connected to the same net from different modules. This is not accepted in the design and you need to fix this issue. It requires RTL correction to resolve this issue. Latches. The latches are not expected in design and during compilation, the tool gives a warning if the design infers a latch. Below are a few reasons why a latch is not preferred in the design. As latches are level triggers and can change the output of an active level of the clock. The latch output is stable only at an inactive level of the clock cycle, due to which the entire clock cycle is not utilized for timing check. Right? So please note that all the commands mentioned in this article are referred from Synopsys EDA tool Fusion Compiler. Conclusion, right? So the article gives an introduction to the synthesis overview, synthesis flow, and the list of checks performed during post-synthesis before it is delivered for physical implementation. It covers the in-depth explanation of each step performed during synthesis. This article also describes almost all the netlist quality checks in detail, such as LEC, timing checks, and other QR checks that qualify the netlist, right? So what we are trying to understand here, right? We are trying to understand the netlist that is getting delivered to the synthesis tool. This netlist, right, is proper, right? For example, if you take GTech netlist, which is intermediate netlist, which is technology independent netlist, this GTech netlist must be optimized properly so that this GTech netlist, when mapped into technology dependent netlist within synthesis, right? So this technology dependent netlist is optimized well, and you can achieve this only when your GTech netlist is optimized properly, which is intermediate netlist, that is technology independent, right? So step one is you need to spend time and make sure that the GTech netlist is optimized properly. Step two, once the GTech netlist is optimized and it is mapped into technology dependent gate level netlist, we need to make sure that the data path is well optimized in terms of power, performance, area, congestion, right? And then we need to make sure that all the netlist quality checks, it can be no clocks, it can be unconstrained endpoints, it can be combinational loops, right? We need to make sure that it can be empty modules as well. We need to make sure that all these checks are performed on the technology dependent netlist before it is delivered to the physical design team. Or if you are going for DFT, then at least for the DFT team, we need to make sure that all these things are taken care, right? Now, once these things are taken care, it means that in physical design cycle, you can easily close on the PPA because your netlist which you are taking as input in the physical design, it is very well optimized. Similarly, make sure that at every stage of the ASIC flowchart, you please make sure that logical equivalence check is done at every stage and it is coming out clean. Without logical equivalence check, we cannot assure that the functionality is retaining same at different stages of the ASIC flowchart, right? from RTL when it is mapped into netlist, and from netlist when it is mapped into layout, right? So how can we make sure that the functionality is retained intact? Only through LEC, logical equivalence check. The synonym of LEC is formality, that is nothing but formal verification. Okay, so once you can make sure that netlist quality checks are properly understood, the commands are understood, and you are using those commands in whichever tool you are using, whether Cadence or Synopsys, right? If you are making sure that netlist quality checks are taken care, then in most of the cases, you can reduce the number of iterations that are needed for closing the design in physical design. Okay, so with this, we'll wrap up the synthesis in VLSI Part 3 presentation from Semicon Technolabs. Stay tuned for more such technical presentations, which we will have again next week. Okay, thank you so much.